And we're on. I'm going to try and go over some answers. Going to go week 6 problems and then week 7 problems. This is the first drawing in the week 6 homework section where the mutual perpendicular to this hyperbolic line through O and this hyperbolic line. So the two hyperbolic lines were given, and then the construction of the only hyperbolic line that's perpendicular to both was done. So the first thing to do when you want to do mutual perpendiculars is the radical axis, which is an easy construction. All you do is lay your ruler across the two intersections. Scoot. The two intersections of the two circles right there. That's radical axis. Such a nuisance. All right, so let's draw this thing. It's good. I need it to intersect that diameter because that's the other hyperbolic line. This other hyperbolic line doesn't, in a sense, have a radical axis, but on the other hand, the radical axis can be thought of as the hyperbolic line itself. I will get that compass back from that weasel. So these guys are going to intersect over here somewhere. On the regular screen, they intersect pretty quickly. Oh, he's such a weasel. So this point right there, that's going to be the center of the hyperbolic line that is perpendicular to both this circle and this line. So let's pause. All right, so let's talk for a second why this hyperbolic line is also its own radical axis. When you have a circle that contains a hyperbolic line, the radical axis is the intersection of the boundary circle and the hyperbolic line circle. Well, this is like a circle. It's like if we took this red circle and pulled these points further and further apart. So if we pulled these points further and further apart, you see this green line would become this extended diameter. So it's the radical axis because it's through the endpoints where the hyperbolic line meets the boundary circle. So where the two radical axes meet, that's the point C. That's going to be the center of the desired circle. It's going to be a pretty big circle because it centers over here. It's going to go like this. And it's going to go in here somewhere. So we need to do the segment that joins A to C, because we have to build a thing called an auxiliary circle to get the right structure. So I'm going through A all the way to C, and there's that segment. I need to make the circle that has a midpoint in here. It's got to have the midpoint in here. I'm going to make a circle that does this. And that will tell me where to put the point of my compass, the pencil part of my compass. So I need to get the midpoint of this thing, which is going to be a tough construction. Let me see if my compass is long enough. It has to go more than halfway. And this compass is too short, so I'm whipping out my big compass. So the construction is going to be, I'm going to do more than halfway. I'm going to get marks above and below from each end. And then I'll have the perpendicular bisector. Hang on. So I use my compass to make these X marks above and below. So now I've got the midpoint. All I care about is that midpoint because I'm going to make a circle. So I'm going to mark using my stuff. This should be the midpoint of the segment AC. So if I put the point of my compass on that point, and I hit the point A, I should be able to make a line. And here we go. Hitting that point A, I should be able to make. All I really care about is this point right here. That's the point where the mutual perpendicular is going to go. So I'm going to go over here and I'm going to catch that point and I'm going to make something that should be a hyperbolic line. So that's a hyperbolic line that's mutually perpendicular to both of these given lines. And it looks pretty good. If you notice, you've got something that looks like a right angle here, and it looks like I got a right angle here where the things hit. And of course I have to have a right angle here because that's where you can tell you've got a hyperbolic line. So that was that construction. Then there was the question was, about the angle CMA. Let's mark who CMA is. There's C, there's A. This is the point M right here. This is M. So the Euclidean angle, CMA, exists inside of, let me finish drawing this thing. This was, remember that was that circle that has, this thing as the diameter. The angle CMA does this. Here's the MA side, here's the CM side. Remember it was undrawn, but notice this right triangle, it's a right triangle because it's inscribed in a semicircle. It's inscribed in the auxiliary circle. So this is a right angle, and if you notice, it's got a radius of a hyperbolic line and a radius of this circle here, the big circle. It's got a radius of that circle. Well, that means that this, this thing that I wanted is a hyperbolic line. And it's perpendicular to the red circle. That's what I really wanted, was perpendicular to the red circle. That right angle tells me that since I have a radius of one circle perpendicular to a radius of another circle, those two circles are perpendicular. So I've got a hyperbolic line and it's got a mutual perpendicular there. It's perpendicular to both this diameter and that red circle. All right, there was a question that was bothering one of the students, and it was, how does the Pythagorean theorem fail? Why does the Pythagorean theorem fail in hyperbolic geometry? And the answer that you have to give is that the Pythagorean theorem, its proof must depend upon the parallel postulate. Let's see one of the famous proofs and see that this is actually the case. This is how you support your argument. You can't just say something, you have to support it. So here's a typical proof of the Pythagorean theorem. You take a right triangle with sides little a, little b, little c. So it's a right triangle, but you don't know that little a squared plus little b squared equals little c squared. You don't know that yet. But you take 4 copies of that triangle and you place them as I have here. Now, if you do that, an interesting thing happens. This angle that I'm going to mark with a single arc and this angle that I mark with a double arc happen to be complementary. Those two angles have to add up to 90 because the 3 angles of a Euclidean triangle add up to 180, and I have one angle being 90 already. So this angle and this angle have to add up to 90. Well, here's a straight angle with 90 degrees accounted for. That means that the red angle on the inside has to also be a right angle, which gives me a square on the inside. And now if you do, the area of the big green square is a plus b squared. And it's also equal to the sum of this square, which is just c times c, plus 4 copies of the triangle that has base and height AB. So 1/2 base times height. So these two things must be equal. Well, this is a squared plus 2ab plus b squared, and this is c squared plus 2ab. Well, you can subtract the 2ab from both sides. That's a very famous and easy proof of the Pythagorean theorem. But notice it used that the angles of a triangle have to add up to 180. That proof depends on the parallel postulate. So this proof depends on the parallel postulate. We don't have that version of the parallel postulate in hyperbolic geometry, and that's why the Pythagorean theorem fails, because its proof requires some reference to the Pythagorean theorem at some point. So that was what I was looking for that answer, was some connection. How do we know that the Pythagorean theorem is going to fail? Is because, here's a proof, for example, that has to use that the 3 angles of a triangle add up to 180, which we don't have in hyperbolic. So we're not going to have Pythagorean theorem. Another question on that same page was, is it possible to have two 50-50-50 triangles, hyperbolic triangles, that are different sizes? And we don't have similar triangles in hyperbolic geometry. You have to use this word. So you can't have 2 triangles with 3 angles of 50, and they're actually different sizes. There's only one size for the side of each triangle that's 50-50, 50 at each angle. There's no other sizes available. There's no other triangles available. We don't have similar triangles. You got to use that phrase. Sorry. Here's one from week 8 that was bothering people. We did something like this in class, but apparently the notes weren't taken carefully enough. So the question was, is triangle JHN, let me shade that for you, is that triangle congruent to triangle GHD? And the student gave the following answer. Said that, okay, you've got radii, hyperbolic radii, because that's the hyperbolic center. H is the hyperbolic center. So each of these dudes is the same hyperbolic length. No question. Of course they are. They're all hyperbolic radii of this circle. Then we have hyperbolic vertical angles right here. Sure. Hyperbolic vertical angles are also the same size. However, and here's the difference from if you had taken notes more carefully, this little segment here, JN, that's not on a hyperbolic line, it's on a hyperbolic circle. This green circle is not perpendicular to the boundary. That's not a segment. It's just a piece of curve. Same thing with GD. It's not a piece of hyperbolic line. So these things are not congruent triangles because they're not triangles. Oh, and I said in the question, I said this is a tricky problem. Now in class on the board, if you go back to your notes, I would hope you would see that I said if you have the hyperbolic line through these two. Okay, so you'd have to have a circle that's perpendicular to the boundary going through the points J and N, which there is such a thing. And you'd have to have the hyperbolic line through these two, and it would look something like this. So these triangles, not including these extra pieces that just don't count, these two triangles would be congruent because now each side is a hyperbolic line. When I say a question is tricky, I'm not joking around. That was a good problem, but you should have spotted it. And that's answers to questions that were bothering you guys.